All right, thank you so much for having me. Thank you for that introduction where you revealed more about me than any introduction has before. I've had a great time talking with folks here today, and I look forward to telling you about some research that I've been doing in my lab for the past, however long my lab has existed. And the research that I'm going to tell you about is about how people make predictions in the social world. And the world that we live in is social. We are constantly surrounded by people. But there's this problem of other people in that we can never really understand what's going on in somebody else's mind. If you crack open the head of another person, metaphorically, of course, you'll find that there is an incredibly rich and varied array of states that that person can be experiencing, everything from love to skepticism to frustration to hunger. And we never get to feel what it's like to be inside somebody else's mind. We know what it feels like for us to experience love or hunger, etc., but we can never understand what other people are experiencing in real time, the richness of another person's experience. And yet, as we walk through the world, we successfully do this. I'm able to understand what it means that you feel hunger or that you feel love. So how do we solve this problem? How do we get inside other people's minds so successfully, despite there being an infinite gap between my own consciousness and somebody else's? So how is it that we're able to think so successfully about other people's internal, invisible mental experiences? So I'm going to try to answer this question, and the analogy that I'm going to follow for most of this talk is an analogy of physical space. So if we're trying to understand where somebody lives, what somebody's location is in physical space at any one moment, we could define a map based on a series of dots arrayed here, and if I wanted to know, where is Santa Barbara relative to Los Angeles or to Denver or to New Jersey, I could say, it's this far, get all the different relations between all the different cities and have some huge matrix of how far away every city is from every other city. But that would be a really highly inefficient way to represent space. Instead, what we can do is organize physical space in terms of latitude and longitude with just two numbers, instead of one number for every distance metric between every single city. With just two numbers, immediately we have a really precise and computationally tractable and efficient way of representing physical space. So how do we represent other people's current mental state? I'd like to suggest that we do this by simplifying the vast array of infinite states that another person can be experiencing into a much more psychologically and neurally plausible set of dimensions. So in the first part of the talk, I'm going to tell you about our endeavor to kind of map mental state space. But that just lays the groundwork for the question that I'm actually interested in, which is how do we predict other people's future mental states? How do we use this map to start making predictions about how other people are going to think or going to feel? But we'll start with the first question. How do we represent other people's mental states? And it may seem silly to think about other people's vast, rich experiences as something that can be as simply defined as with two or three dimensions. But this is actually very well-trod territory within social psychology. Psychologists have been trying, since psychologists has existed, to simplify the structure of the mind for quite some time. One of those dimensional theories is the theory of arousal and valence, which says that if you want to capture what emotion somebody is in, all you need is these two dimensions of valence and arousal. How good is someone feeling? How intense is that feeling? And this theory has done an incredibly good job at capturing a lot of important things about how people feel emotions. It's not the only successful theory out there. There's another way in which psychologists have carved mind space into two dimensions. Here, agency and experience. These two dimensions, likewise, have been incredibly valuable to psychologists for understanding how people are thinking and feeling in the world. But there's other very successful two-dimensional theories out there as well, warmth and competence. Here, this one, pretty good. good at defining more group level things, but we can also think about an individual at various levels of warmth and competence, and on and on. So we scoured the literature. We found, what is this, seven really great ways in which psychologists have thought to carve up this space of mental states. And so we have a good kind of foundation for trying to understand what are the latitude and longitude of mental state space. What we also know from decades of social neuroscience is the neural networks that are involved in thinking about mental states. So this set of neural regions are involved reliably when people are thinking about what another person is thinking or feeling. They are reliably active, at a greater level than when you're thinking about, floors or chairs or dogs or walking. But we don't know very much about what the representational structure is, what the topography of this activity is that allows us to represent other people's mental states. So in that respect, social psychology is ahead of neuroscience in suggesting what the parsimonious structure might be for representing other people's mental experiences. But what we can do is we can leverage these two levels of analysis to start answering and testing hypotheses about how people think about other people's minds. And the way we do this is as follows. So each of these two-dimensional theories generates hundreds of hypotheses about how the brain should be representing other people's mental states. It does this as follows. So if you array every mental state along agency and experience based on reliable ratings from people about how much that state reflects agency versus experience, you find that self-pity and affection are very similar to each other. They're very close together in this space, whereas skepticism is further away in this space. Other dimensional theories make other hypotheses. So according to valence and arousal, self-pity and skepticism are the ones that are similar to each other, and affection is the one that's the outlier. So there's tons of hypotheses here about how similar or how different each mental state should be to each other. And we can test those hypotheses using the brain. Which of these dimensions successfully captures how people are actually thinking about mental states? So the way we test this as follows. We have all of the mental states rated on our dimensions. We can generate a behavioral similarity matrix, which simply says how far away are each of these states from each other on this dimension, come up with our matrix. Then we generate a neural similarity matrix for every state. The way we do this is we put people in the fMRI scanner for quite some time, and they think about mental states. So on one trial, they might be asked to think about happiness. Their task is to decide which of two scenarios is better at eliciting happiness. We don't care what answer they give. We just want them to be thinking about this mental state in a wide variety of scenarios. So they think about happiness. They think about alarm. They think about every state that we could come up with, optimized with various optimization parameters that I'm not going to go into now, but I'm happy to answer questions about. There were 60 states that we looked at. Every run included one trial for each state. There were a total of 16 runs. So over 16 runs, we had people thinking about happiness and alarm 16 times across a wide variety of states. So with that, we can generate a reliable pattern for happiness or for alarm or for the other 60 states. And we can, using the kind of topography of these patterns, look for how similar the pattern is for happiness as it is for alarm, simply by correlating the vector of those patterns. With that, we can get a matrix which tells us how similar the brain is representing each and every one of these mental states. And these matrices allow us to test the hypotheses generated by each of the dimensions. So here, valence. If these two matrices align, that suggests that what the brain is doing when it's thinking about these mental states is it's taking into account valence. We do this for valence, and we do this for all the other dimensions, which each have their own set of predictive matrices. The four dimensions that we're going to test are these four. So I told you originally we had 16 or 14 dimensions that we gathered from the social psychology literature. Turns out a bunch of them are kind of redundant with each other, which is nice. Social psychology has kind of converged on similar ideas about what matters when we think about other people. We did a dimension reduction over them and found 4 reliable dimensions. And so these are the ones that we tested against our neural data. So rationality here takes into account whether or not something is high in emotion or experience or high in reason or competence. Social impact is kind of the convergence of things that are both social and high arousal, so things that are really impactful in our social world. Valence is simply whether it's good or bad, and human mind is whether or not it's something that is uniquely experienced by humans or can be experienced by all animals in their bodies. So what happens when we look for the correlation between the hypotheses made by each of these dimensions and the neural patterns of activity while our participants were thinking about mental states? What we find is that 3 of the 4 dimensions do a really nice job of capturing the patterns of activity that arise in people's brains when they think about other people's mental states. In this study, they did such a good job that they captured about 50% of the reliable neural variance in our participants when they were thinking about mental states. So what we concluded from this study is that the structure of mental states, the kind of latitude and longitude of other people's mental states, is defined by 3 psychological dimensions: rationality, social impact, and valence. We're calling this the 3D mind model because there's 3 dimensions about minds. We've since done a number of studies testing the robustness of this model. 4 studies which all had people thinking about other people's mental states. And what we find across all of these studies in a meta-analysis is that each of these 3 studies overall does a really great job of capturing how people are thinking about mental states in terms of the neural hardware that they use to think about mental states. So much so that when you account for individual level variance and methods level variance across the studies, we're capturing 80% of reliable variance in neural pattern similarity, which I think is doing a really good job of capturing how people are thinking about these states in a way that I didn't even think was possible. When Mark Thornton, my collaborator on all of this work, told me this, I told him he had to go back and make sure that there wasn't a mistake because I didn't think social psychology could give us such reliable answers. We've also tested the robustness across different cultures. In one analysis, Mark Thornton scraped millions of tweets, English tweets from all of these different countries, and looked at the extent to which, using kind of vectorized word analyses, looked at the extent to which our dimensions could capture the way in which people are using emotion terms in the language. And what we found is reliably, across just about every single country that we looked at, except for Rwanda, we are doing a significantly good job of capturing the way in which people are using language around mental states. We compared our model to kind of the best alternative, which is the 2-dimensional circumplex model, and found that in the majority of countries, we are outperforming that model. So from here, we suggest that the structure of mental state space seems to be stable across all of these cultures. Now, all these cultures were using English, and they were on Twitter, so it's not a random sample. So we also looked at 17 different languages and the way in which they use their mental state terms. And what we found is, again, the structure of mental state space is stable across languages, across these 17 languages that we looked at, except for Japanese for 2 of the dimensions. I don't know what's going on with Japanese. We also looked across time. So we extracted from Project Gutenberg historical texts in English and in French. After a conference talk that Mark gave, a scholar of Chinese, ancient Chinese, came up to him and was like, we've got to look at ancient Chinese. So we looked at ancient Chinese. And across all of these historical eras and cultures, we found, again, our 3 dimensions are doing a really nice, robust job of capturing how the language is talking about mental states. So we find overall that the structure of mental states is incredibly robust and stable across time and space and cultures. Okay, we have this model of how people think about other people's mental states. We have our latitude and longitude of mental state space. We've kind of tried to answer this question. I think we've done a good job of doing so. But again, answering this question is not my main goal here. My main goal here is to answer this question, the question of why we represent other people's mental states, with the hypothesis that people are representing people's mental states in order to predict what they're going to do. Yeah?
Clarification. I was a little confused about the different things, because at first you were having people in the scanner sort of experience the states, and then you said about people doing something about somebody else's mental states, and then when you started talking about the language, because how are you getting the similarity of mental states from language? I don't know how to
I
put together.
completely skipped over the methods of the linguistic analysis. I can give you a brief.
And if you could say a little bit about the content of these dimensions, because right now they're just labels, right?
Yeah. 2 questions. Okay, so I'll do the first. So the way that the language analyses work is there's these kind of word-to-vec and fast text kind of analyses that can take all of the language that you give it, so an entire corpus of language, and kind of see what the co-occurrence of each of the words are with each of the other words. So it creates this huge matrix of how each of the words kind of co-occurs with different words. And you can do a dimension reduction on that huge co-occurrence matrix, and they reduce the entirety of the language based on this co-occurrence matrix to 300 dimensions. And what we're looking for with this 300 dimensions is how similar or different two words are in this new 300-dimensional space. In the 300 vector space that was defined based on the co-occurrence matrix. So an example of things that you can do with this.
Why would that give you the similarity? I mean, I could say,
So let me tell you. So one thing you can do with this method is things like analogies. So in this method, if I give you the vector for king and the vector for queen, the difference between those 2 vectors is the same as the difference between man and woman. So something about these 300 dimensions is capturing kind of the use of words in our language. And so the way that we do this with mental state words is we look at the vector for happiness, and we look at the vector for alarm. And we can see how different, what the kind of cosine distance is between those 2 vectors. And what we'd expect is if the language is capturing, is kind of encapsulating valence, when we're talking about mental states, then 2 states that are close together on our valence dimension should have vectors that are not very far apart from each other, that have kind of a small angle. 2 mental states that are far apart on valence should have a larger distance. And that would be evidence that the language is in some way capturing what our dimensions are capturing. And so that's the data that I'm showing you there for the language. So our dimensions are represented in this kind of high-dimensional language space. And then your question was, what are these dimensions? Sure. So valence is simply something good or bad. So happiness is good, sadness is bad. Social impact is this a state that is of high arousal and relevant to the social world? So things like lust and envy and dominance, all high arousal and relevant to the social world, whereas things like sleepiness or fatigue, not very social, very low arousal.
Could there be things that are low arousal but highly relevant to the social world?
So those would be somewhere in the middle. We didn't actually predict that those 2 dimensions would align so well. Turns out that there is something about the way in which our states are experienced, which makes social experiences more highly arousing than non-social. I think that's a whole interesting question in and of itself, why those 2 align so well, but that's what the data showed us. And then the last dimension is rationality. So I've been talking about these mental states and emotions kind of interchangeably, but what the rationality dimension suggests is that we make a distinction between things that are more felt, so emotions, versus things that are more cognitive. So thinking, judgment, those would be on the high rationality end of the dimension, whereas things like happiness, sadness, those would be on the low emotion. All right? Okay, so we have our 3-dimensional space, and we think that what we can do with this 3-dimensional space is predict what other people are going to do in the future. I'll give you a toy example of how this should work. So we have accessible to all of us the observable action layer. We have access to seeing what other people are doing in the real world. So let's say I see someone raise their hand. I can make a prediction about what action they're going to produce next based on all of the talks I've been to and the kind of stimulus-stimulus associations that I've built up over my lifetime. So current behavior allows us to predict future behavior, and we do this all the time as we're walking through the world. But as humans, we have access to this additional layer of information, the hidden mental state layer. And our 3 dimensions gives us access to understanding how things work in this layer. And the way that I think this works is that current states allow us to predict current behavior. So there's many mental states that might produce the action of raising the hand. And if I know what state you're in, I might be able to predict what kind of behavior you're going to engage in. States do us one better than just getting us kind of the current action. I think they can help us get further into the future. They can help explain with more nuance what is going to happen in the future so that I can prepare accordingly. I can answer a question differently if I know it's stemming from hatred than if it's stemming from intrigue. So this is one of the ways in which representing mental states can be exceedingly powerful. They give us a glimpse into the observable social action layer well ahead of their occurrence. But I'd like to argue that states do us even one better if it's the case that states predict states. So if there's reliable patterns of transition from one state to the next, then if I know that you forgot to eat your breakfast this morning or drink your coffee, you might be in a more negative mood, which might lead to a more negative question than if you successfully drank your coffee and are well attentive. So in this case, knowing what someone's state is gets you kind of 3 steps into the future. And then, of course, we have another hidden layer that us humans have access to and are especially attuned to, which is the trait layer. If I know someone is smart, I know they're likely to be more attentive, more intrigued, and ask smarter questions. So each of these layers gives us information about what other people are going to do at kind of different frequencies of analysis. So here's the kind of toy model that we're playing with. We have access to someone's mental state that gives us access to information about what action they might produce and their future mental state and future actions and so on. We have the trait layer, which informs us at all of these moments. And what I've told you so far is what the structure of this mental state layer looks like. I've focused on this structure so much to explain how people represent mental states, because it lays the foundation for our primary hypothesis, which is that the structure of mental states helps us to make predictions in the social world. So the structure that defines our kind of concept for emotion is tuned by the goal of prediction. So in this next part, I'm going to show you evidence that we've started to accumulate for this hypothesis. All right, so we have our map. How do we predict other people's future states? The idea is that the structure has layered on it information about the kind of roads that people are likely to take. So if I know where you are right now, I should be able to predict where you're going to be soon by knowing which roads exist and kind of which paths are more well-trod than others on this map. So if these roads are reliable and perceivable, then current states should predict future states. And moreover, the structure of the mental state model should allow us to make these transition predictions. And this is because you're much more likely to move closer by in the space than farther away in the space. If I'm currently in Santa Barbara, I'm much more likely, or maybe you're much more likely to next go to LA than you are to Kansas. Okay, so we'll start by testing this first kind of sub-hypothesis, which is whether or not we even can predict future states from current states before we test whether or not our latitude and longitude get us there. So to test this question, first we got a lot of data about how people experience mental states over the course of the day. We did this by borrowing other people's data. So a number of studies, a fourth one here that I'm not showing you, which all shows the same thing. So all of these studies have wonderful researchers who were willing to share their data with us. They did experience sampling on their participants at various time frames for various lengths of time. In all the cases, they were asking participants in real time, how are you feeling right now? They asked them, how are you feeling on a number of different sets of states, all generally within the kind of emotion part of our spectrum. So with this data, what we can ask is, are there reliable transitions that people are likely to make? Are there regularities in this transition space from one state to the other? And I'll show you the matrix of the to state to the from state, which looks like this in study 1, like this in study 2, and this in study 3. Now, you could spend all day looking at every individual box here. I recommend you don't do that because it will give you a headache. The main thing to take away from these matrices is that there's color on them. There is reliable information in people's current state about what their likely future state is. So current states do indeed predict future states in terms of people's actual experienced emotion transitions. What we don't know yet is whether people actually pick up on this information and use that to make predictions about other people's states. So the roads are there. Do people know where the roads are? To answer that question, we ran 3 parallel studies to each of these experience sampling studies, where essentially we asked people, for every one of those squares in the matrix, what's the likelihood that you think, if a person is currently in state A, that they're next going to be in state B? We did this independently for each of the studies, asking them for every single from state to every single to state. And what we want to know is, here's our experienced transition matrix, what people actually experience from moment to moment. Is it the case that when people are making inferences or making predictions about how people are likely to transition from state to state, do they do so accurately? Now, to do that, we ran 2 parallel analyses. So first, here is the group level analysis, the group level data for people's kind of intuitions about how people transition from state to state. What you can do is simply get the correlation between the group level rating matrix and the actual experience transition matrix. And what you find is that there's a nice high correlation between the two. You can also look at how people are doing on an individual basis and take the correlation between every individual's matrix and the group level experience matrix. And what you find is overall, almost everybody gets a correlation above 0. And on average, people are having a pretty high correlation of 0.53. And we replicate these findings across all the studies that we looked at. So people do have a good intuition about where the actual roads are on this map. So next I want to turn to how people make these accurate state-to-state predictions. And again, the hypothesis here is that people are using these 3 dimensions in order to do so. The way we tested in which people are using these 3 dimensions is as follows. So we know what people think the transition probabilities are between every state and every state. We also know, based on readings, where people think these states are on valence, social impact, and rationality. And the hypothesis is the further away 2 states are on any one of these dimensions, the less likely they should be to transition between them. So Santa Barbara is far from Berlin. People should be less likely to transition from Santa Barbara to Berlin than they should be to go from Santa Barbara to LA. And that's exactly what we find. The further away 2 states are on each of these dimensions, the less likely they are to actually experience a transition between the 2, and to infer that another person is likely to experience a transition between the 2. So we find that our 3D mind model, our 3 dimensions, nicely predicts state transitions, both people's actual transitions in terms of their the experience sampling data, and people's inferred transitions in terms of the rating data. So much so that if you run a mediation analysis looking at what explains the relationship between people's actual transitions and the inferred transitions, you find that there's a mediation via our 3 dimensions. We also find that these 3 dimensions explain how people represent transitions in the brain. So if you look within a predefined set of regions in the brain at how people are representing each of these mental states, what you find is that the more similar 2 states are, the more likely there is to be a transition between the 2. That is, when you're thinking about someone's current state, you're kind of already thinking about what their next state is going to be. And that helps us make these kind of automatic and spontaneous predictions about what other people are likely to feel, because current states are already kind of predicting the pattern of what the likely next state is going to be. So our 3D mind model is doing a nice job of predicting state transitions, both actual transitions, inferred transitions, and the transitions that we represent in our brain. So where are we so far? Current states predict future states. People are accurate about predicting those future states. The brain is spontaneously encoding these state transitions. And we do all of these by leaning on this three-dimensional map of mental states. So we have our mental state map. And I've been talking about this mental state space as an organizing framework for our state knowledge, just as latitude and longitude allow us to organize our physical map. So does our three-dimensional mind model help us organize our state knowledge. And the roads on this space tell us which paths are more well-trod than others, and so which transitions are more likely than others. However, the structure of the United States, where the grounds are for Santa Barbara and where the grounds are for LA, existed well before we built roads on them. So a person is more likely to transition, to move from Santa Barbara to LA than from Santa Barbara to Berlin, because they happen to exist in a proximal location. So here, in terms of physical space, the state structure determines the transitions. But this is where our map metaphor breaks down. Instead of the state structure coming first, and that allowing you to predict transitions, in the case of mental states, what I think happens is we have state transitions, which come first, and the state structure is built around it. So it's not the case in the real world that people were traveling a lot between LA and Santa Barbara, and so the United States decided to organize itself such that those two things were close to each other. But that's what I think happens when it comes to mental states. So people, instead of using the structure of the map to make predictions about mental state transitions, I think people generate the state map. They generate their concepts of mental states by observing state transitions. So this might seem like a wacky hypothesis. I'll show you exactly how it might work. So imagine you observed the following transitions in another person. All right, do you have a sense for how this person kind of moves through state space? So this set of transitions was drawn from a transition matrix that looks like this. And if you're a person who is observing these state transitions, you might build up what is an accurate model of these transitions. And if you did so in a very parsimonious way, your model of this person's likely transitions might look something like this. You can see that this representation has a coherent geometric structure. It's a circle. People are highly likely to go from state 1 to 2 to 3 to 4 to 5 to 6 and back to 1, with some low level of likelihood of transitioning to a different state in the matrix. So we start by observing transitions in the world. Here are 36 pieces of data about how a person might transition from state to state. 36 pieces of data that people need to keep track of. A mind that tracks these transitions might then represent the states using this directed graph. And once you have this directed graph, you no longer need to keep track of every single transition. All you need to keep track of are the locations of these states and the kind of proximity between the states. And you can calculate the proximity. So in this proximity graph, state 1 is closest to 2, is closest to 3, 4, 5, 6. State 2 is also close to 4 and 6 in a way that you might have predicted from the transition structure. And then you can extract from this now geometric representation a kind of proximity matrix based on our new understanding of this state space. This proximity is calculable, and now we have our distance matrix. And it's this distance matrix of how similar or dissimilar each state is to each other that reflects people's concepts of state space. And so this is how you might go from transitions to structure. So we ran some studies to test whether or not this is possible. We had people observe a series of transitions, not state 1, 2, 3, 4, 5, 6. That would be maybe hard to keep track of. Instead, we told people you are an alien psychologist, a psychologist of aliens, not an alien who is a psychologist, an alien psychologist who goes to a new land, and your job is to observe their emotions. And you observe their emotion transitions, say as follows, from Bembit to Tentum to Parpak, Kalfas, Gepkin, Itzel, and so on for 100 trials. You observe these transitions over and over. The transitions are drawn from a certain transition matrix. And after you've observed these transitions, you're asked, how similar is Bembit to Tentum, Tentum to Bembit, Bembit to Parpak, and so on for every single one of those 30 similarity judgments. So the question is, what information are people drawing upon to make these kind of conceptual judgments? We've given them transitions. Is it the case that seeing only transitions, people generate a kind of conceptual map of where these states are, and then use that the geometric proximity of each of the states within that map in order to make their predictions? What we find is, yes, indeed they do. So people do use the transition probability matrix, but above and beyond that transition probability matrix, they're using what they've extracted from these transitions as the geometric proximity to make their judgments. So here we find, in this interesting contrived scenario, that people can go from observing transitions to a conceptual understanding of these states. So people learn mental state concepts from mental state dynamics alone. So the next thing we wanted to know was, is this something that's possible in the real world? Is it possible that people can go from the mental state dynamics that they observe in the real world? So here's one full matrix of 60 states to 60 states, which we've gotten reliable ratings on. What happens when people observe these? And moreover, when they observe these, can we extract dimensions of their new geometric structure? And do those dimensions map on to the ones that we've thought are the ones that define people's mental state structure? So we didn't have people observe these states. They've done that already in their real world, and they've shown us what the structure of mental state space is. Instead here, we taught a computer what the transitions are. So we generated a sequence of 1 million states from this transition matrix. We trained a neural net with kind of a 3D embedding to predict the next state from the current state. That's what its job. Every round, we fed it one new state. It had to predict what the next state was. It does a pretty good job of predicting future states. It gets to about a B- in terms of accuracy by the end of training. So it's learned how to predict states. How does it do so? Well, in order to figure out how it does so, we can look at the 3D embedding that it's learned, that it's kind of tuned. This is 2 of the dimensions of the learned embedding. And we can ask, to what extent does this learned embedding correspond to what we think are the dimensions that define people's mental state representation? And when you look at the kind of axes of this 3D learning embedding, we find that they correspond incredibly well with our 3 dimensions. So rationality, social impact, and valence are all highly significantly correlated with the way in which the computer optimally learned how to predict transitions. Evidence, I think, that mental state concepts can arise solely from observing real-world mental state dynamics. As if the way in which we understand the latitude and longitude of mental state space is a result of having observed just the dynamics of states from moment to moment in other people or in ourself. Now, that's not to say that there's not other features of mental states that might also inform this map. We've done other studies where we kind of pit a transition matrix against features. So there are features associated with mental states. If someone's happy, their face is going to be contorted in a particular way, and that contortion of musculature is going to be more similar to some states than others. So there's kind of visual features that we can extract about people's states. There's physiological features about people's states. So all of these are kind of features that people might have access to about other people's states. So we in our kind of alien paradigm, we pit features of the alien transition, the alien states against a simple transition matrix. So there was 2 clusters in terms of transitions, and there was 2 clusters that were completely orthogonal in terms of features. The features here were the color of the alien's eyes, drawn from kind of the blue cluster and the red cluster. And what we find is, indeed, people are picking up on the feature of the state, the visual feature. But they're above and beyond that, they're defining their conceptual structure of state space also based on just the dynamics that they've observed. So again, I think this is nice evidence that we need to put the dynamics of emotions on the map as a foundational piece of information that people are using in order to build up their conceptual understanding of people's emotions. Okay, so let's step back again and see where we're at. So we have mental states that predict actions, and future mental states, and future actions, and so on. I've shown you that the structure of this mental state space is defined by 3 dimensions. The structure is incredibly reliable across all of the different ways in which we've looked at it. We've also looked at it in terms of thinking about one's own states versus other states, and we find that the structure stays the same, but the size of the space kind of expands and contracts. So overall, all of my states are very different from each other because each of my states is a special butterfly, whereas your states are maybe a little bit more similar to each other overall. The structure of this mental state space is determined by the transitions that we observe in the real world. There's also this trait layer that I haven't talked about. We have a little bit of work showing the way in which the structure of the trait layer is related to the structure of the mental state layer. There's 3 dimensions that also define the trait layer, and they're highly corresponding to the 3 dimensions of the mental state layer. So much so that we found that if you add up all of the mental states that somebody experiences, weighted by how often they experience those states, you can recreate the patterns of activity that define that individual person. So an individual person, their traits, their identity, etc., may simply be just the sum of the experiences that they've had. What I haven't told you about at all is this action layer. The action layer is the ultimate test of the hypothesis, and our hypotheses do need to be cashed out in terms of the action layer for us to be able to say that we're doing anything that actually buys us something in the real world. So I'm going to give you a little bit of a whirlwind tour through the work that we've been doing to map out the action layer and how we've been trying to see in a parallel way to the way that we've looked at mental states whether or not the structure of the action layer also buys us information about people's future actions. So the structure of the action layer is much more complex than mental states. There's about 300 mental state terms that we've identified in the English language, and there are about 10,000 verbs in the English language. This is kind of cluster of all of the verbs in the English language. You can see there's a lot, but there's some structure there. If you look, zoom in, you see all of the kind of cooking-related verbs are near each other. So we've done some work that I'm not going to go into methodological detail for to figure out what the structure of this action layer is. We find 6 reliable dimensions: anancy, creation, tradition, food, abstraction, and spiritualism. Comes with a nice acronym, ACT FAST. Here's what each of these dimensions do. We've kind of figured out that this 6-dimensional structure is nice and robust across a lot of different kinds of data. We can use it to capture information that people might want to know about actions, particularly socially relevant information about actions. So we looked at whether or not locations on these dimensions can help us predict things about like who is likely to do an action, where they're likely to do an action, when they're likely to do an action, how they're likely to do an action, and why they're likely to do an action. And overall, in each of these 16 pre-registered hypotheses, our taxonomy successfully predicts people's judgments about the who, where, when, why, and how of actions. So we think we have a solid action taxonomy. We want to know, can we use this action structure to predict things about future actions? The way in which we've tested this is a number of neat data sets that we've collected on action sequences. One of those that I'll show you is from the WikiHow website. I don't know if you've ever been there, but anything that you want to know how to do, it will give you a sequence of actions about exactly how to do it. Anything. You can learn how to do anything. So what we did was we scraped these sequences of actions from WikiHow and then looked at whether or not the proximity of each of these actions, operationalized here as verbs, the proximity of those verbs on our dimensions predicts how likely it is that they will follow each other in this sequence. And for each of the 6 dimensions, we find that they do a very nice job of predicting how the actions will flow in sequence. We've since replicated this in 3 other data sets, so you can look at the scripts of movies, and we see also that our dimensions do a nice job of predicting the sequence of verbs in lines of the script. There's experience sampling data from, or kind of daily recall data from the American Time Use Survey, where people report what they've been doing over the course of the day. And then there's video data from Google, where people are engaging in a series of actions. And in all cases, our 6 dimensions significantly predict what the action sequence is likely to be. We've also looked at this in naturalistic stimuli. We had people, my colleague Uri Hassan had people lay in the scanner while they watched the first episode of Sherlock. And from there, we have neural data about how people are processing the actions that are on screen. We can use a computational vision algorithm to label the actions that are on screen at any time. And the first thing we wanted to do is do our 6 dimensions capture what action is on screen at time 0, when we're actually looking at the neural data. So here we kind of, again, this is kind of glossing over a lot of methodological detail, but we can figure out where in our 6-dimensional action space the brain is representing at any one time. And then you can see whether or not that brain state corresponds to where the action is that is on screen at that time. So that's what I'm showing you here at time 0. We find that we can decode what the current action is on screen significantly and successfully. What we want to do next is see whether or not where someone's brain is representing within the 6-dimensional space, can it predict what the next action is going to be? And indeed, it can, up to about 3 actions into the future. Where someone's brain is representing right now, if they're representing the current action, that gets us 3 steps into the future in terms of future actions. So we can do this from actions. We can also do a similar analysis from states. If we just decode what state someone is representing on screen at one time, we can decode both the current action that they're viewing, as well as future actions up to 5 states, up to 5 actions in the future. And here's where we kind of see that extra leverage that the hidden layer buys us above and beyond the observable action layer. When you combine these 2 things, you find that people are doing significantly better at predicting future actions than they were by just looking at what the information was based on actions alone. So here we have this kind of three-layer model of predictive social cognition. You can read more about it in our theory piece. about how people kind of structure their action, their knowledge at each of these different layers in order to make predictions, both within that layer and across the layers. There's obviously many, many more things that we need to figure out about this model. I'm sure you have questions or suggestions about that. One thing that we're looking at next is context, or the situation that people are in. So far, we haven't looked at kind of situations whatsoever, but we know that the situation that someone's in has a huge impact on what they're feeling and what they're likely to do. But that will be for next time. The summary for now is the social knowledge that we have in each domain that we've looked at is tuned for social prediction. So with that, I want to thank my lab, my primary collaborator on this work, Mark Thornton, and all the other collaborators and funding that have helped make it happen.